I'd like to pass over now to Thomas from Copenhagen Atomics. The title of Thomas's talk is Thorium Molten Salt Breeder Reactor as a Waste Burner Using Heavy Water as a Moderator. Thomas, the floor is yours.
All right. So in Copenhagen Atomics, we have similar long-term perspectives as everyone else to solve the energy needs. We even say that energy is required to have prosperity in the society, and most of our employees have these T-shirts. There's been a lot of misunderstandings around thorium, so I want to make some clarifications in the first few slides. The unique thing about thorium is that it's the only element that can create a breeder reactor in thermal spectrum. And you cannot make all these great or get all these great things from thorium if you use them in traditional reactors. There seems to be some misunderstandings in many articles about that. You really need a molten salt reactor where you can remove the fission products in order to have all these great things that thorium allow in the fuel cycle. And then, of course, we will never run out of thorium, and we call it a renewable energy source. And then people say, "Oh, it cannot be renewable like wind and solar." But on the same time scales as we will run out of materials for wind and solar systems, we might run out of thorium. So it is really a renewable energy source on the same scale as wind and solar. Copenhagen Atomics is all about mass manufacturing of molten salt reactors, basically manufacturing them on an assembly line. We have set up the system so that we could manufacture one reactor every day on an assembly line. Our reactor has less components than a modern car, and we're already operating in such a factory where there were mass manufacturing of similar systems before. If I should make a quick summary of Copenhagen Atomics in these 5 bullet points, we have made a system that can translate into a molten salt breeder reactor. And because of this, we can generate electricity at very, very low costs. And I will get back to that. We believe that the electricity cost that we can provide at when we get to mass manufacturing of reactors will be lower than any other energy source, including all the fossil fuels and fusion and whatnot. The thing is that we can take spent fuel and we can burn that in our waste burner. And when we do so, we get 10 times more energy out of that fuel than what the traditional light water reactors were able to get out of the same amount of fuel. So that's quite significant. And that's really the promise of thorium combined with breeder reactors. We wish to sell our electricity, or not, we wish to sell our energy as energy as a service. We wish to build, own, and operate the reactors. And essentially, we are selling the heat from the hot salt, and then we want partner companies to either convert that into electricity or use it for industrial heat or desalination or many of these other applications that have been talked about in previous talks today. Copenhagen Atomics is already building our first prototype reactor in Copenhagen. We're actually going to build several prototypes full scale in these shipping container sizes. The first one has already been working with testing with water, and we're going to test the next one quite soon with FLINAC salt, but I'll get back to that later. And then finally, we have sort of a very, very long-term goal that we would like to supply green energy to 1 billion people. A lot of people always ask us, but I assume also many of the other people, companies here in this call, what is the main application going to be? And of course, we've looked at a number of these different applications, and we've had discussions with potential customers in all these areas. The one that we favor is the one at the top. So new built molten salt reactors or new built power plants on land. I know that there's a number of other companies looking at either refitting coal-fired power plants or putting reactors on barges or even putting them on ships. And I think it's great that we're trying to attack these different markets and different sectors, and there different companies are trying to find solutions for these different areas. When we have looked at this in the past for our particular reactor design, we have come to these conclusions around prices and market sizes. So this is our view on the on how fast this can be deployed and how readily available the fuel supply is. When we compare molten salt reactors, or especially our version of the Copenhagen Atomics waste burner, to some of the traditional energy systems, we see that if you compare energy input to build those systems versus the energy output over the operation of that system's lifetime, we see that wind and solar has very little or very small amounts of output versus input, and even if they were to really incredibly double that or unthinkable triple those numbers, it still doesn't matter in the larger scheme of things. And I think that's also why all of us is on this call, because we realize that we have to rely on gas and oil and coal until we can have a new type of nuclear energy, and that's what Copenhagen Atomics is all about. A little bit of our timeline. I mentioned that before. We've already done the first testing in our full-scale prototype of the reactor with water. We're getting ready now to test with molten salt. That is a FLiNac salt. And then by the end of next year, hopefully, we will be able to do the first test with a thorium salt. We're going to manufacture those salts ourselves. So it's a lithium fluoride, thorium fluoride salt. And then we expect to be able to start the first prototype reactor in 2025. It will not be in Denmark. It will be in some other country. We're already in dialogue with a number of countries about where we can do this. And then hopefully by 2028, we will be able to supply commercial reactors. And once they have been deployed, then we will start starting up the production line. We imagine that our reactors will be deployed in a fashion similar to what is shown in this graphics. So the graphics here show a 1 gigawatt electrical plant, but what is showing there in that building is only the nuclear side of things and the thermal energy production. So inside this building, we have sort of 25 rows, with each one having one of our thorium molten salt reactors, each one of those providing roughly 100 megawatts of thermal energy, or in other terms, sort of 43 megawatts of electrical energy. So 25 of these running in parallel, and then they will send the hot salt over to the buildings there in the background. And over there, other partners will convert that hot salt into steam or electricity or industrial heat or whatever they choose to do with it. Our system is most economic if we can run full power 24/7. In that case, we believe that we can be able to supply energy at $20 per megawatt hour once we are up and running in full production. And you see these reactors in there in the building. They are automatically removed from sort of a very thick containment structure and moved over to the back and stored there until they get ready for recycling. There's no humans inside this building while the reactors are operating. Here's some other pictures of that. Copenhagen Atomics wants to build a thorium breeder reactor that can start on transuranics. And of course, it can also start on other things. I'll get back to that. But a lot of people misunderstand the approach that we're taking. Therefore, I'll just try to explain it here. So when you take spent nuclear fuel from light water reactors and look at those fuel rods, then 95% of the atoms in that spent fuel is actually uranium atoms. And it's exactly the same uranium atoms as what came out of the ground many, many years earlier from mining. And of course, you could say, if it's the same atoms that came out of the ground, it must be a natural product, and that's at least our belief. But of course, the difficult thing here is to separate that in a very clean manner. We believe that we can separate it clean enough that we can provide that uranium back to the global uranium market, and other people can use that for something useful. And then we will take the last roughly 5% and split that further into fission products and all the transuranics. We will then send the fission products for storage, and we believe that they are separated in a way where they only need to be stored for at most 300 years. And the rest is sort of a very dirty mix of things called transuranics, and it includes plutonium, and that's what we want to mix with the thorium in our reactor and burn it down, and I'll come back to the burn up charts, so that it's also converted back into fission products. Copenhagen Atomics have a different development philosophy than most of the other companies presented here today. Most companies have chosen the paper design route. We have chosen a route indicated in blue there at the bottom, where we did a lot of development, basically a lot of testing, a lot of development, and very rapid iterations on improving on our components. And now we've gotten to a point where we've started building reactors. And of course, we want to test the full-scale reactor, even with the right salt. That's lithium fluoride, thorium fluoride salt. We want to test that before we go into the approval phase and get the reactor approved. We also do not go directly for a commercial reactor. We believe that it's more economic and safe, sort of short route to test a 1 megawatt test reactor first, and then move on from there to a commercial reactor. These are some images from our current facility. We have done a huge amount of testing. If you accumulate all the tests we have run on different components, we've now in excess of 70 years of total test hours, and our team is currently 60 people, and we're located in Copenhagen. Here you see some of the pictures. These are the molten salt loops that we use for testing, and we believe that before you can safely operate a reactor, you need to demonstrate that you can safely operate these types of loops for thousands of hours, and I believe that there are still a lot of companies who need to achieve that. We have developed these loops now for 7 years, and we're actually selling some of these loops to universities and national labs around the world to increase the knowledge of molten salt reactors, and also for them to do some of the same tests as we're doing and sort of duplicate that and hopefully get the same results as we get. Copenhagen Atomics is well known for supplying super pure salts. On the left side there, you can see some of our early lithium fluoride, thorium fluoride salt samples. In the middle is a FLINAC bar, sort of a very clean salt bar. And on the right-hand side, you see some of the latest canisters where we put 100 kilograms of salt inside each of these canisters, and they are transferred in molten state to the tanks where they're going to be used. Our current production facility, we produce over 1 ton of very clean salt every month. Those are mostly FLINAC salts, and eventually we will also produce chloride salts and thorium salts and potentially other salts as well. And we are selling these salts to collaborators around the world. We've done a lot of testing on electronics and sensors, and these are some of the images of that. And then, of course, our very famous molten salt pump. You see the pump there at the top image. It's able to run inside the furnace or inside the reactor at 700 degrees, and it's a centrifugal pump where the motor is integrated, so it's called a canned type pump, and the whole motor is running at 700 degrees, electrical three-phase motor. And of course, these pump at the top, we don't plan to get those approved for use inside a nuclear reactor. That's actually the second generation of pump that you see at the picture below. It's an active magnetic bearing pump, which means that all the rotating parts are levitating on a magnetic field, and we believe that we can make that pump run for 10 years without service. And on the right-hand side, you see some pictures of where it's being tested. Here is the picture of one of the reactors. This is the one that we used for water testing. Sort of in the middle, you see a big wall out of stainless steel. Everything to the right of that wall would be the hot side of the reactor, where everything is at 600 degrees. Everything to the left of that wall would be the area where we have the heavy water moderator and the electronics and everything at low temperature. And of course, there's some shielding, which is not shown here. The octagon on the right side is the reactor core. And at the bottom, down below, what you can see is the dump tanks for the salt and the water and so on, pumps, etc. Here are some of the images of all our test loops in operation. We currently have almost 15 loops in operation, and we're building 10 more loops right now. Here are some of the test tubes for testing static salt tests, that is mostly corrosion tests, materials tests, sensor tests, things like that. We have 30 of these test tubes. And then Copenhagen Atomics is also active in making open source software for simulating molten salt reactors, and especially we're helping to make, you can call it digital twins or whatever, sort of very high fidelity CAD models of the reactor experiments, the molten salt reactor experiment, the aircraft reactor experiment, and the zero power reactor experiment, and also the for example, the molten salt breeder reactor, which was never built but has been simulated with a number of other tools, so you can compare the simulations to either the real world experiments or the results from other simulation tools. Yeah, the OpenMC simulation software has come very far, and it's a great tool now for simulating molten salt reactors. So I encourage you to look into that. And also, if you want to use some of these reactor models to simulate in other tools like Serpent or MCMP, then please contact us, and we can work together to establish sort of an industry-wide basis for how accurate these different simulations tools are. Now I'll go into a little bit more technical talk about some of the simulations that we have done.
Thomas, we need to wind this up pretty soon, yeah?
Okay, then I will jump these two slides and just talk about, this is the last 3 slides, and I'll do this quickly. So this first one here show a reactor where we start on plutonium. So this is a reactor grade plutonium, and you can see the blue colors are the plutonium, and this simulation runs on the left side. There is a burn up over 10 years, and you can see how the blue colors, which is the plutonium, are burned up over those 10 years, and you can see how the neutrons are used in the green color. With the dominant green color is uranium-233, and the sort of brown color at the bottom is the thorium. So you can see how it translates into and become a breeder reactor after a number of years. And on the left-hand side, you can see the composition of the different elements in the reactor core. Here is another similar simulation, but in this case, we start the reactor on transuranics. In order to start our reactor on transuranics, we need 200 kilograms of transuranics up front, and then we can start the reactor. And eventually, you will only need to load thorium in order to continue to run. And here is an example where we start the reactor with 5% enriched uranium. And of course, it's a different scenario because it will continue to both breed plutonium from the uranium-238, and it will also breed uranium-233 from the thorium. So it's sort of a mixed reactor, but it just shows you that we can also run the reactor on enriched uranium. So that was all my slides.
Yeah, please go ahead with your question. You need to unmute yourself.
Hello, Thomas. It's Kobi Adulami.
Yes, hi.
Hi. Do you concern about how you get license regarding your system? Because the heavy water is very close to the core. So the regulation, it's not so like this kind of situation.
Yeah, so it's correct that in our reactor core, we have both channels with heavy water that is not under pressure. It's at sort of 50 degrees or below. And then we also have the molten salt at, say, 600 degrees in the reactor core. And it's true that those are very close to each other. There is thermal insulation between them, and there is 2 barriers so if they were to mix, you would have to break 2 barriers. But we've even done tests that if they were to break, we would generate steam, and of course the reactor could not start again in that case, but it will not come outside the reactor box. The reactor is a sealed vessel, and the steam that would be generated, we actually have a system for cooling that down again, and it will not come outside of the reactor vessel, even if they were to mix very much. And I should also highlight here, a lot of people falsely think that the majority of the heat into the heavy water will be this thermal transfer from the hot salt into the heavy water, but that's not true. It's actually the thermalization, or the slowing down of the neutrons, that is the main source of energy that is generated in the heavy water. And of course, we need to remove that heat, and that's actually some of the air conditions you saw on the pictures of the plant earlier.
Thank you.
And a second quick question from Ian Scott. So $20 per megawatt is very impressive. What discount rate or cost of capital did you use in your calculations?
That was a comparison with a sort of a wind and solar farm, and we were using the same discount rate as in that other comparison study. I don't remember on top of my head, but it's likely something like 3%. I should also say that this was made before the current rate hike, but of course we do expect that rate to come down again before we're ready to mass manufacture these. So we've continued to use that number and that study.
Very cool. Thank you, Thomas.